Okay, so my name is Guilherme. I'm going to talk a brief discussion in transformers for image recognition. The article we're going to talk about is called "An Image is Worth 16 by 16 Words: Transformers for Image Recognition at Scale." It was developed by the Google research team in 2020. The outline for the presentation, I'm going to give a brief context about the goals the article is trying to achieve, the relevance it has on current computer vision tasks. Afterwards, a brief introduction about transformers and CNNs, that's convolutional neural networks, the method, so the vision transformer, about the paper, the experiments they did, a brief summary, and the references. So the context they are developing into is they want to prove that transformers can be applied to solve computer vision tasks. For example, common computer vision tasks nowadays can be classification, that you want to classify a single image into a single label. So for example, if you want to identify an animal, here in the first picture you can see the classification being done as a cat. Can be also detection, that you want to know where the animal is located in that picture, and segmentation, that you want to know specifically which pixels specify that specific animal. And they also want to prove that these transformers for image recognition can perform better than convolutional neural networks, because these convolutional neural networks are the most used for computer vision tasks nowadays. The relevance, why they did this article, is given the context that transformers for other fields in machine learning, specifically NLP, that's natural language processing, were becoming very, very popular. So since the first installment of Transformers in 2017, its popularity was growing very, very fast. And they wanted to know if that knowledge could be applied to image recognition. So in 2020, they developed what they call the visual transformers, that want to adapt the transformers architecture to solve computer vision tasks. The first installation of this architecture wants to use a pure transformer, so they don't use any kind of convolution layers or any kind of other neural networks types, only transformers, to just use as a baseline for proving their methods. The pros of using transformers in image recognition is that attention is a very it's very integrated in the transformers network, so attention can be more used than regular CNNs. The high scalability, so when using more and more data for training, the model will not overfit and can be still be generalizing the performance. Although the cons is that using transformers to outperform CNNs require a lot of data sets, so sometimes providing large data sets for image is quite a tough task. And it also has a high computational cost, but not as high as CNNs. Here we can see the popularity graph of CNNs. So one of the first CNNs that was developed was LeNet in 1998, and nowadays we can see that there is this ResNet CNN that I'm going to talk more about in later parts of the presentation. It has become more and more popular. As you can see, other models that were trying to compete with ResNet became integrated with it, because its characteristics can achieve better performance and accuracy in the majority of the tasks. So I'm going to give an introduction of transformers and a brief introduction to CNNs. So transformers are a field in the NLP, so we are working with text. This is the transformer architecture. We have multi-head attention, then feed-forward. This is a block for the encoder part of the transformer, and that information can be then passed to the decoder part, so this part right here, that also provides attention and gets that attention from the previous encoder blocks. So as you can see here in this GIF, there are multiple encoder blocks, so this part right here, that feed information into multiple decoder blocks. So the information that is obtained from here is also passed through multiple blocks, so that that information is always kept inside the network. Also, we have the positional information of the token. So since we are working with text, normally we wouldn't have a specific order. So in images we have like the position of the image that can be relative to the position of the pixel that can be relative to another pixel. But in text we don't have that information, so we have to provide some kind of positional information that shows where the sentence starts and where it ends, and that we will have this positional encoding that artificially represents the position of each token in a sequence. And we also have residual connections at each block. So here we can see that the input also is utilized after the multi-head attention step. So it has a combination of both the resulting product and the previous step. So a brief introduction to convolutional neural networks is that we have convolution layers that they are learnable feature extractable layers. So they want to extract the best features from each input. I have pooling layers that want to reduce this dimensionality. So this step here, you can see that the feature map is reduced in size. And it also wants to extract the best information from that feature map. And afterwards, we have the dense layers right here that want to get all the best information that you came up with in the upper part of the network and just make a classification out of those upper information that you achieved. So talking about the paper in specific, this is the architecture they are proposing, the vision transformers. They want to utilize the theory that's behind CNNs, that to use the whole image and have its positional features still in place. So they divide the images into patches and enumerate each of those patches with a sequence that it's an artificial spatial representation of where those pixels are. So the transformer architecture has that positional layer as shown in the transformers architecture. Afterwards, they apply a class embedding in the zero position. That's a learnable token that wants to learn what class that image is representing. So we are working with image classification in specific. Also, we have still have the multi-attention head. So afterwards, after each of the patches is projected, we pass it into a transformer layer, and we have a multi-attention head into it. So each pixel is equally representative in that patch. So we have interdependence within the pixel and its other neighboring pixels. Also, we still retain the residual connections inside the transformer block. They developed 3 base VAT models that they purely used transformers. Those are called the bit base, the bit large, and the bit huge. The only difference is the number of layers of transformers encoders in each of them. And they also follow a notation that represents how big the image is divided before passing to the transformer encoders. They also developed one hybrid model that wants to utilize the first convolutions layers of the HasNet architecture, but afterwards they only use the transformers, so they want to know if it's good to combine like both of the models to retain like the best of both worlds. So the experience they did to compare each of those models, they trained their models into two data sets, the JFT data set and the ImageNet 120K data set. Both of them are very, very large data sets, more than 1 million images they needed to train. And they used as baseline the BitL and the noisy student. BitL is a model based on the HasNet architecture that I said previously. And noisy student was another state-of-the-art data set that was the best model for one of those data sets they provided a study with. And BitL was chosen as well because in the other data set it is the state of the art as well. And here we can see that the huge version of the VAT model outperforms any of the other two models that they use as baseline, but it's a bigger model, so it's compared to itself, to its other models. It takes a lot of computational power to train, but comparing the other two that are similarly large to the BTL and the noisy student, we can see that sometimes, depending on the data set they are trying to compare with, it can achieve similar results, but more importantly, we have lesser computational resources that is required to train those data sets. So we can see that using transformers, we have a reduction in training time. Other results they achieved were, this is a comparison here on which training data set they use to train each model. So as you can see in the square ones here on top, those are the bit ones, so they use as baseline, and the circles is the transformers models. You can see that when using lesser images, this dataset ImageNet, not the 21K, has less images. The BIT model, so the CNN, outperforms the transformer. So we can see that the model is very related to how many images we have to train. And afterwards, you can see that the VAT starts to outperform it. Here, this is also this is the same graph, but training using the other dataset, the JFT. So how many of those images the model has seen at a specific time. And also we can see that at the beginning, both of their HasNets, so the CNNs, outperform, but after seeing about, like here, the 50 million mark of images, the transformers start to outperform them. Here we have a study of the models they developed. So it's just a comparison between the variance of size of the VAT and the hybrid. They also plot the VAT to like keep it as a baseline, but they use different sizes of this model. So each block is a different size, and we can see the total pertaining compute flops that is required. And at the beginning, we see that the VAT is outperforming, and the hybrid also is outperforming at the beginning. But afterwards, once we have seen enough data, the transformer period architecture starts to outperform both of them. So we can see the scalability that's related to using purely transformers. And here we're going to see evaluation of their article, and also like how the article was important to us nowadays. So today, on their article, we can see that using a lot of data sets, so a lot of images, the bigger model achieved easily state-of-the-art benchmarks on multiple data sets. It can be very, very versatile because specifically we are talking about image classification, but few modifications have to be made to be done to using other tasks, so object detection or semantic segmentation. And the gains that they provide over CNNs is that they have global information, so each pixel, because of the attention modules, we have information on how this specific pixel is related to the other pixels in a global way. We have less computational cost to train, so regarding hardware restrictions, we are less demanding, but we also have the problem we need to use more data set to train to achieve a better result, and we also have less inductive bias. That's because CNNs inherently use the spatial components of the image, so it uses where that pixel is placed specifically and how it's related to its nearing neighbors. But now we are seeing the whole picture. We are seeing like the information more globally. Also, they provide an example of inferences that they made, and specifically where the model is paying more attention to. So here, when we want to classify this image as a dog, we can see that the model focuses only on the dog object, and here as example for the plane. The last image with the snake, it got a bit confused, but we still can see that it still has a bit of attention regarding here, and the background starts to be not as important. And the summary of importance, nowadays many architectures using transformers for image recognition are being developed. So here is a graph that displays the number of tasks that is developed using VAT. So it's tough to see here, but these are two different blues in the graph. So we have 50% used for image classification, 40% for object detection, 3% for image denoising. No, that's 2% for image denoising, 3 for image segmentation, 1 for compression, and 1 for super resolution. This is a table that a survey in 2022 provided that shows how many VAT-based models are developed nowadays, and this table is only for this 50% part, so image classification, and you can see that it's very, very much used nowadays. We have a lot of different variants, so CV, CrossFit, and they all perform very, very good in their regarding problems. And this is the reference that we made. This is the article. This is the Transformers article, so the original architecture, the survey that they developed, and another group developed, and another survey that they used. So that was it.
Thank you very much. So basically, the authors state that vision transformers are a better alternative to CNNs if you have enough data.
Yes.
Right? So the first question concerning that is, why doesn't the transformer suffer from overfitting, or would it also suffer from overfitting? You just need much data.
It doesn't suffer as much as like regarding overfitting because the self-attention layers they preserve the like what is the model trying to learn. They don't try to focus on the data itself. They try to focus of how the each not token, because now we're talking about images, so how each pixel is related in general to to its other pixels. So they're not focused of, for example, in CNNs, we are focusing on how to extract the data. So if we provide too much data or we don't have any function to prevent this overfitting, the CNN will be specific to that data set and how it can extract that information from there. But the transformers one, it won't be as related to that. It will be more related to how those pixels are correlated to each other. So it will not be dependent on the data, but dependent of how the relations between them.
And I mean, one of the benefits of CNNs is that you can quite easily use transfer learning. So
Yes.
the first layers are pretty much learned on a huge data set,
Mhm.
and then you just retrain the last layers. Is something similar possible for the vision transformer?
Yeah, it's also possible. Not specific for this article. I'm doing research in another article. They have a transformer-based network that was trained on ImageNet, but afterwards it was specifically applied into a medical data set, so it can be easily transfer learnable. But in this article specifically, they don't talk about using that because they were the first ones to develop visual transformers, so they didn't have any basis to come up with that. But they cite that that was a continuation, natural continuation of this research.
And so nowadays there's a rise of these AI-based chatbots like ChatGPT, and they are called generative transformers. This is basically the same technology underneath, or do you know?
It depends. I'm gonna go to the beginning because I think here, yes, we have IGPT, that's NLP transformer for image pre-training. I think here they are trying to get a text input from a user, and from that input they develop an image. So basically what they're trying to do is, I don't think I have a good picture for that, but basically they have an encoder that will encode the information, the text information, and afterwards that from that information that extracted from the encoders, they try to decode it into an image. So these parts are not, they don't have to be in the same domain. So this can be the text domain, and this can be the image domain, or the other way around. Like you get a picture and it extracts a text out of it. So it's not dependent.
Questions from you? And maybe I have one last question. You showed those attention images.
Okay.
Showed where the network pays attention to.
Yes.
How are these images actually created? So how do they know where the network pays attention?
Yeah. This was not developed by them. They said in the article they are using like a Python library to get attention from the inference they are making. So it's not like the how you can see in CNN. So it's not like the feature map that is extracted, or the feature extraction layer. It's more like which pixels were more used to make the inference. Makes a bit of sense. It's not like that much specified in the paper, but they comment that they did not develop this. They only provided an example for this.
Good. No more questions? Does anyone need a short break? No? Okay, then let's first speak again.